Welcome to The Explainer. Today, we're talking about something that isn't just a piece of math, but a deep, fundamental rule the universe has to obey. It's a cosmic trade-off that shapes everything, from the sound of my voice to the very first moment of time, and it's all driven by one powerful idea.
So let's start with a simple question. Think about sound for a second. Could you create a sound that happens in a single, perfect instant, but at the same time has a pure, clean musical pitch, like a perfect middle C? Is that even possible?
The answer is a definite no. You absolutely can't. And the reason why tells us something profound about how reality works. See, a sharp clap, boom, it's perfectly precise in time. But musically, it's just a messy burst of pretty much all frequencies at once. On the other hand, that pure musical tone, well, it's perfectly precise in its frequency. But to be that perfect, it has to last forever. You simply can't have it both ways.
This cosmic balancing act is run by a mathematical engine called the Fourier transform. It's the official rulebook for these complementary pairs, and the rule is simple. The more precisely you define one property, the more blurry and uncertain the other one becomes. It's a fundamental limit on what the universe will let you know.
Okay, so this is a cool idea for sound waves, but here's where it gets truly wild. This exact same principle isn't just for things we can hear. It's the core operating system for the bizarre world of quantum mechanics. And this leads us to probably the most famous example in all of physics, Heisenberg's uncertainty principle. It's the same trade-off all over again. A particle's momentum is kind of like its frequency. If you manage to pin down a particle's location with perfect precision, its momentum becomes a complete blur. And if you measure its momentum perfectly, then good luck finding it, because its location is now completely spread out. So here's the really crucial part. Position and momentum aren't two separate facts you can just write down about a particle. No, they're more like two faces of the same quantum coin. They are just different ways of looking at the same underlying reality, and they are locked together forever by the Fourier transform.
All right, so this rule governs sound, and it governs tiny particles. But let's zoom out, way out. What if this principle applies on the biggest scale imaginable? What if this same trade-off is built into the very fabric of the cosmos itself?
We've seen how this fundamental trade-off applies to the world of sound.
And we know it's at the very heart of quantum mechanics. But here's the really big leap. What if this isn't just about little waves and particles? What if the very fabric of space-time, of reality itself, is also playing by these same rules? Well, there's a fascinating new theoretical model called the Conformal Emergent Reality Model, or CERM, that proposes exactly that. It suggests there's a radical, new kind of pairing at the very foundation of quantum gravity. At its core, this model introduces a brand new quantum uncertainty relation. It says there's a fundamental trade-off, a new Fourier pair, between two massive concepts. One is called prototime, and the other is the curvature of space-time.
Okay, let's break that down. First, prototime. Don't think of this like the time on your watch. It's something more fundamental, a basic ordering of events. You can think of it as a geometric clock that actually ticks faster where space-time is more curved and gravity is stronger. And the other half of the pair is curvature. This is straight out of Einstein's playbook. It's simply a measure of how much space-time gets bent and warped by matter and energy. It's literally the geometry of the universe. So, we now have a new uncertainty principle that links the order of events to the geometry of space. And if that's true, it has absolutely profound consequences, starting with the biggest puzzle of them all, the very beginning of our universe. You see, according to general relativity, our universe exploded from a single point of infinite density and infinite curvature. We call it a singularity. But really, infinity is just physics screaming that the math has broken down. The theory can't cope. But now, let's bring in our new uncertainty principle. What would happen if the universe tried to create that singularity? A perfectly sharp, instantaneous spike of infinite curvature. Well, the Fourier transform would step in and say, not so fast. If you make the curvature of space-time perfectly precise and sharp, its partner, prototime, has to become infinitely blurry and smeared out. You just can't have a perfectly defined curvature at a perfectly defined moment in time. And just like that, the problem is solved. The universe physically prevents the singularity from ever forming because it can't be pinpointed in time. The Fourier transform blurs out the very moment it was supposed to happen, replacing an impossible point of infinity with a fuzzy quantum cloud of possibility.
And believe it or not, the consequences get even stranger. This idea reaches down and messes with our most basic understanding of cause and effect.
Remember, if the order of events, that's our prototime, and the geometry of space, that's curvature, are a Fourier pair, then you can never know both of them perfectly at once. Down at the tiniest, most fundamental scale of reality, there's always a trade-off.
And this leads to a truly mind-bending possibility. It means that at the Planck scale, there might not be a single definite before and after. The universe could actually exist in a quantum superposition of different causal orders. Before and after get smeared out. Causality itself becomes fuzzy.
So, the big takeaway here is that the Fourier transform isn't just a clever bit of math we came up with. It appears to be a physical constraint on information, a fundamental law that's baked right into the fabric of reality, shaping everything from a simple sound wave to the entire cosmos. This completely reframes how we look at the universe, not as a collection of separate things, but as a deep web of these complementary properties. And it leaves us with one heck of a question. If time and geometry really are two sides of the same quantum coin, what else is? What other fundamental pairs are out there, quietly shaping a reality we're only just beginning to understand?